enter left stage.
The photoelectric effect was evidence that light or energy acts as a particle. So let's talk about what that means. So usually I ask a student to come help me when I'm explaining this, but since I don't have any students in person right now, I'm going to use my son instead. So if I throw a bunch of little photons at him, Ruben here is an electron. So I throw a photon, throw another photon, another photon. I mean, I could throw birdies at him all day, little photons at him all day, but nothing's gonna happen. And that's because the energy in a single photon or single birdie, it's not big enough. It's just, he might get annoyed, but he's not gonna fall over. I'll use you again in a second. So this is completely different from other experiences you may have had. So if you've ever been to a water park, right? And the thing now is every 15, 20 minutes, they make everybody get out of the water to rest. And that's because that energy is a wave, right? And the waves are constantly pounding on you when you're standing in that wave pool. You don't get rest. So the concern is, right, the waves are wearing you down, and eventually you could potentially collapse, you could become dislodged, and, drown. So there's a big difference in the energy associated with a wave or the energy associated with an individual singular event. This energy is not building up. It happened, it's over. I throw the next one, it happens, it's over. Versus a wave has energy that builds up. So that was one part of it. They were like, well, if no electrons are being ejected when we have a low energy light, then that must mean it's not acting like a wave. So then they established this idea of a threshold frequency or a work function. So the work function, phi, basically is the minimum amount of energy necessary to dislodge an electron. So what does that mean? And if I can bother you again, Ruben. All right, this time I'll use a little eraser to represent a really, really small photon. So if I throw the little eraser at him, nada, right? Like he didn't move or anything. And we want to dislodge him, right? We want to see him move from his current position. And that's what they were trying to do. Hit the metal with the photon, and we want to see the electron be ejected. So I'll grab a slightly bigger photon and throw it out. Again, not big enough to cause him to fall over or become dislodged. Let's try a soccer ball. Alrighty, so nothing. Even though it's quite a bit bigger, it still didn't have enough energy in that singular event to dislodge him. So what about this rock? I can barely lift it. What if I threw this rock at him? Ready?
No.
Okay, let's do a dramatic reenactment then. I got the big rock, I throw it at you. All right, so he pretended to fall down, or he actually fell down for the purposes of this video. So if the photon becomes big enough, it has enough energy, then it will successfully eject the electron. Maybe if I threw the rock at him, he would just fall over. But at this point, I always ask the students, well, what if something really, really big came flying at you, right? Bigger than the rock. Has anybody ever been hit by a car? And it never fails. There's always like a student or two that has been hit by a car. Last semester, I actually had a student who was hit by a car in the Palomar parking lot. So just be careful when we come back to school. Anyhow, if you get hit by a car, unfortunately, if the car is going fast enough, not only do you get knocked out of off of your feet, you also potentially go flying through the air. So that helps explain what's going on with this equation here. If you have a big enough photon, some of the energy is going to go into the work function, which is the energy required to dislodge the electron. The excess energy beyond that, delivered by that singular photon, is going to go into kinetic energy or energy of motion. So we could break this down a little bit further and set kinetic energy equal to 1/2 mass times velocity squared and solve for the speed at which the electron is going to go flying. So there's a lot we can do here with some of the ideas behind the photoelectric effect. So the take-home message from earlier is that energy acts like a particle. It can't build up like a wave would and eventually become enough to dislodge the electron. There has to be enough energy delivered by a single photon if we expect an electron to come off or be dislodged. So in our first problem here, they tell us that the energy required to dislodge electrons from sodium metal is 275 kilojoules per mole. So it's going to be per mole of electrons. And they want to know what wavelength has sufficient energy per photon to dislodge the electron. So the key here with that second statement is they're looking for the wavelength to dislodge a single electron. And right now the work function has units of moles of electrons. So let's get rid of that. So we know 1 mole of electrons has 6.02 times 10 to the 23rd electrons. And then while we're at it, we'll also fix the kilojoules. So we'll turn them into joules. So here I got 4.5681 times 10 to the negative 19 joules. And so we have a work function with the correct units now. So the energy of the photon has to be greater than or equal to the work function to dislodge the electron. We know from Planck's equation that the energy of the photon is equal to hc over wavelength. And then we have this value. So we'll plug in the 4.5681 times 10 to the negative 19 joules right here. I'm going to cross multiply to get the wavelength in a single line. So at this point I have h times c is greater than or equal to 4.5681 times 10 to the negative 19 joules times wavelength. And now I can plug everything in. So h, it's still that same Planck's constant. So I'll use 6.626 times 10 to the negative 34 joules times seconds. Since I'm solving for wavelength, I'm not going to put the photon piece in there right now. It doesn't cancel with anything, so it doesn't really make any sense. And then speed of light, 2.998 times 10 to the 8 meters per second. And I'm going to bring over the wavelength, so I'll divide this whole thing. I'm not going to bring over the wavelength. I'm going to bring over the work function, so I'm going to divide this whole thing by 4.5681 times 10 to the negative 19 joules. And that's going to be greater than or equal to our wavelength. So h times c divided by our work function, and I got a value of 4.34858 times 10 to the negative 7 meters. And we need to convert that to nanometers. So I'll multiply that by 1 times 10 to the 9th. Let me set that up real quick. So 4.35 times 10 to the negative 7 meters. 1 meter has 1 times 10 to the 9th nanometers. So we get 435 nanometers. So at the end of the day, we want our wavelength to be less than or equal to 435 nanometers. And you might be like, well, why do you want the wavelength to be less than 435 nanometers when you're trying to create a photon that's big enough to eject the electron? Remember, there's that inverse relationship between wavelength and frequency, right? And we could solve for frequency here as well using C equals lambda times frequency. But as this number gets smaller because of the less than, then the frequency, which is associated with our energy, becomes bigger. So therefore, that's why that answer there kind of seems wrong, but it is correct. Alright, so in this problem, we're given the work function for silver metal. It's calculated at 436 kilojoules per mole. And remember, when they give the values like this, it's per mole of electrons. So I'll take care of that first. I'm going to convert it to just joules. So 1 mole of electrons has 6.02 times 10 to the 23rd electrons. And 1 kilojoule has 1,000 joules. So kilojoules cancel kilojoules, moles of electrons with moles of electrons. And I'm left with 7.24 times 10 to the negative 19 joules. Alrighty, I added a second part to this question. Originally, the question just asked us what frequency of light is needed to eject an electron, and we'll work on that first. However, after that, we're going to go with this hypothetical situation where the metal is exposed to a photon with an energy of 1.3 times 10 to the negative 17 joules, and we're going to calculate the velocity of that ejected electron. So let's go through part A first, the frequency of light. So we know that the energy of the photon, in order for it to be dislodged, has to be greater than or equal to our work function. In this situation, they're interested in frequency. So for my energy of the photon, I'm going to use Planck's constant times frequency is greater than or equal to the work function. And then I'm just going to, well, I'm solving for frequency, so I'm going to divide each side by Planck's constant, which means our frequency has to be greater than or equal to the work function divided by Planck's constant. So let's plug and chug and generate that value. On top, we'll have 7.24 times 10 to the negative 19 joules. And then underneath, I have Planck's constant. So the 6.626 times 10 to the negative 34 joules per second. In terms of our units, joules will cancel joules, and we're left with inverse seconds. That's perfect because frequency has units of inverse seconds or hertz. And in this case, I get 1.09 times 10 to the 15 hertz. So that's the frequency that we would need to eject the electron. So we'll work on part B. This time we're given the energy of the photon. And I'm going to relate that to both the work function and the kinetic energy. So if I do the energy of the photon minus the work function, that will allow me to solve for the kinetic energy, or the energy of motion associated with that electron. So the energy of the photon is 1.39 times 10 to the negative 17 joules. And I'm going to subtract the 7.24 times 10 to the negative 19 joules. And I get 1.3176 times 10 to the negative 17 is my kinetic energy. At this point, I can use the fact that kinetic energy equals 1/2 mass times velocity squared. A couple things here. One, it's going to be the mass of the electron. So I'll put a little e down there. The mass of the electron is a universal constant, and you can look it up in a textbook or it's in a lab manual. That's something that you can find very easily. It's going to be constant. The other thing is we want to keep that in kilograms. Joules, we've been using joules. It's a derived unit, and it's equal to kilograms times meters squared over seconds squared. So as I set this up and start plugging stuff in, I'm going to change my units over here, the joules, to the kilograms times meters squared over seconds squared, so I can see how everything's canceling. So I'm copying my kinetic energy from before, put my new units, and I want to divide that by the mass of the 1/2 times the mass of the electron. So 9.1093897 times 10 to the negative 31 kilograms. This is going to give me velocity squared. Be careful too on these. The second thing I forgot to mention was there is a difference between frequency and velocity. One is the Greek letter. So our frequency, right, is more like script. And then the velocity has a really sharp point at the bottom. We see this in future problems as well, where we have velocity to deal with as well. All right, so kilograms, we cancel kilograms. And then I'm left with meters squared over seconds squared, which is fine because I still got velocity squared. So velocity squared equals 2.8928 times 10 to the 13 meters squared over seconds squared. And so you're going to take the square root of both sides. And when you do that, you get a velocity of 5.38 times 10 to the 6th meters per second. I torture him today. Let's hit him with a soccer ball and see if anything happens.
Ow.
Sorry. But still, the point here is, and I know you guys can't see his feet, but it didn't knock him over. I didn't mean to hit you in the face. I'm sorry. So if I take this rock and I throw it at him, no, I'm not going to throw a rock at you. But if I threw a really, really big rock at him, right? What do you think would happen?
I'd crack my head open and fall over.
Okay, let's pretend I'm throwing the big rock at you. Do a dramatic reenactment of what's going to happen. Okay,